Bismillahirrahmanirrahim. Assalamu alaikum. In this lecture, we'll also continue the discussion that we had begun a few lectures ago about the DC-AC converters, or also known as inverter circuits. In the first two lectures, we had introduced the inverter topology, or the basic concepts about the inverter circuits, the classification of voltage source inverters, that is, it is having three different types. The PWM inverters, square wave inverters, and single phase inverters with voltage cancellation. Then in the last lecture, we elaborated the basic concepts related to switched mode inverters, the different operating area for inverter, in which it can work either as inverter or as rectifier circuit. Okay. Then we had that basic one leg of switch mode inverter circuit. We introduced how it works, okay, and how it can be used as a basic building block of any inverter topology, leading from the very basic half bridge inverter to complicated three-phase inverter types. Okay. Then in a separate lecture, we had introduced the operation of half bridge and single phase full bridge inverter circuits, but in that case we did not discuss about the switching mechanism. So in the last lecture, we also discussed quite in detail the very popular pulse width modulation switching scheme, and in that we described that how is the switching of individual switches performed in any of the inverter circuits. Okay, we introduced the basic terminologies related to that, the amplitude modulation ratio, the frequency modulation ratio, and how these can be used to regulate the output voltage as well as the frequency of the output inverted signal. And we also discussed the effect of having a small frequency modulation ratio or a large frequency modulation ratio. Okay, we also discussed the range for which the amplitude modulation ratio has a linear relationship with the fundamental frequency component of the output voltage. Okay, that is called the linear range of operation for this parameter. And then we also discussed the over modulation range, that is when the value of this amplitude modulation ratio exceeds 1, and in that region now it's no more having a linear relationship with the fundamental frequency component of the output voltage. Okay, and then even when we extend this value, or when we increase this value way beyond a particular number, that is 3.24, so now this system enters into the square wave mode of operation. That is, for this particular case, the output will be having a duty cycle of 0.5, that is, will have only a positive and a negative pulse of the output voltage available for this particular case. Okay, so based on these concepts, now let us extend the discussion to the single phase inverter circuits. Okay, in the case of half bridge inverter circuit, as we'll see its figure over here, this is basically that same circuit that we have already discussed, which is basically the one leg of switch mode inverter circuit. Okay, so this is effectively a half bridge, termed as a half bridge inverter circuit. Okay, so there is not a lot difference between the discussion that we had already for the BWM application of this circuit and the current one. Okay, so it's not required to be explained any further. Okay, in this particular case, for each of the half cycle or for during the switching of each switch, okay, that is T plus and T minus, the output voltage will be switching between Vd by 2 plus Vd by 2 and minus Vd by 2. Okay, moving forward to the full bridge inverter circuit that we can see over here in this figure 8.11. Basically what we have done in this particular case, that two one leg inverter circuits, or we can also say that two half bridge inverter circuits have been combined to make this single phase full bridge inverter circuit. Okay, the main advantage of this inverter circuit as compared to the half bridge inverter circuit is that now the output voltage switches between plus VD and minus VD. Okay, so in this particular case the output voltage is twice compared to that of the half bridge inverter circuit. Okay, so what does this mean? This means that for the same amount of power the output current will be one half of as compared to that of the half bridge inverter circuit. Okay, so for high power inverter circuits this is a clear advantage. Okay, that for the same amount of power transfer the value of output current will be one half of that of the half bridge inverter circuit, and since that same current which is being provided to the output or to the load is passing through these switching elements. Okay, so that makes like the use of these switching elements to be of relatively lower rating as compared to the ones that we'll have to use in the case of a half bridge inverter circuit. So in the case of half bridge inverter circuit, if you just want to draw the waveform of the output voltage, so what we will have that it will be pulsating between this will be VD by 2 and minus VD by 2. This is for half bridge inverter circuit. While in the case of a full bridge inverter circuit, what we will have, we'll have an output voltage which is equal to VD and minus VD. Okay, the reason for this is that in the case of full bridge inverter circuit the equation or the point of measurement for the output voltage is VA naught minus VB naught. We'll just see that in the figure in a while as well. So if you want to calculate it, the relative difference of the 2 points, so that makes it equal to like VD by 2 plus VD by 2, that makes it equal to VD. So this is how during this interval it will be equal to VD, and similarly for the other case these will be interchanged, so we will have this minus VD. Okay, so for the same amount of the power to be transferred, since the output voltage is double as compared to the half bridge inverter circuit, so it means that the output current that would be required to flow through the switches in the case of full bridge inverter will be half of that as compared to the half bridge inverter circuit. Okay. Now let's move on to two different types of switching schemes. We have already discussed and described the pulse width modulation switching. Now within that we are having two distinct categories. Okay, one is called bipolar voltage switching. Okay, so we need to focus on this term for this particular case. Okay, so now what does this mean? So we have already discussed this scheme, but now let us link it to this full bridge inverter circuit and have the discussion of these two schemes. The next scheme that we will be discussing, that will be PWM with unipolar voltage switching. Okay, so in connection to a single phase full bridge inverter circuit, we'll see that what is the difference in each of these schemes, and what do we mean by bipolar and what do we mean by unipolar, and for a certain particular application which one of the two PWM schemes is more advantageous. Okay, so if we just quickly recall, so we had a full bridge inverter circuit. Let me quickly redraw that over here for quick recall and onward discussion. Okay, we also had these anti-parallel diodes, okay, for each of them. And is another pair of switches. Okay, and in this particular case, this is called point A, and then we have this point. They are of course connected. This is point B, and the output voltage is across these 2 points. Okay, direction of the current flow, and as I had mentioned, V naught is equal to VA naught minus VB naught. Okay, and this is the point O. Here we have a high value capacitor, so that the input voltage is equally distributed across these 2 capacitors. Okay, this is the input voltage, this is the input current for us. Okay, we just quickly label these switches. We will have TA plus and A minus. Okay, so what happens that the diagonally opposite switches, that is like this one and this one, TA plus and TB minus, these are turned on simultaneously at the same time, and then the other pair of diagonal switches, that is TA minus and TB plus, are turned on at the same time. Okay, these are turned on in switch in pairs. Okay, so with this type of switching scheme, the output voltage waveform is same as we had in the basic one leg inverter or the half bridge inverter. Okay, what we had done, if you remember the discussion that we had last time, basically this is the same concept that we had discussed about the pulse width modulation. Okay, but we had not described whether it is a bipolar voltage switching scheme or a unipolar voltage switching scheme. So in fact, that discussion that we had was about a bipolar voltage switching scheme, in which we had we had a triangular wave. Okay, and then we had a sinusoidal signal for comparison. Okay, so this was the triangular waveform and this was our control signal. Okay, if you remember that discussion, in that we had these conditions that when the control signal is greater than the triangular waveform, so then in that case this first pair of switches will be on and the output voltage will be equal to plus VD by 2. Okay, and then when this control signal is less than the triangular waveform, then this other pair of switches will be on and the output voltage will be equal to minus VD by 2. In fact, these potentials are at these measurement points. If we have a closer look, let us say that we are having this scenario. Okay, then the first case, so what happens in that case, that let us say if this pair of switch is on, okay, and then the diagonally opposite switch, this one, is on for this particular case. So you can see that this point is connected all the way to this particular point, and the potential at this point with respect to this point, that is what we call VA naught. Okay, that is equal to VD by 2. Okay, and similarly with the potential for this negative or reference point of the output voltage, this is all the way connected to this particular point. Okay, and if we take the potential of this point with respect to O, so that is in fact equal to minus VD by 2. Okay, so now if we take the difference of these two, that gives us an output voltage that is in fact equal to VD. Okay, or we can also say that this is a double that of what we had in the case of single leg inverter or half bridge inverter. This is what we had in the half bridge inverter circuit. So now this is in fact twice of that we had over here. Okay, sorry, we have 2 over here. So this is what will make this half bridge inverter circuit like having an output voltage half of the full bridge inverter circuit. Okay, so the previous analysis that we carried out for like this particular case is applicable over here, and the rest of the discussion that we had quite in detail, that is the fundamental, the peak the fundamental frequency component, the peak amplitude of the fundamental frequency component of the output voltage is linearly related with this amplitude modulation ratio, provided that the value of amplitude modulation ratio is less than 1. Okay, and if this is greater than 1, then we have this other equation, that is now it is somewhere in between this one. Okay, 4 by pi into Vd, this is the maximum value of that. Okay, and in this particular case, as I have mentioned quite a while ago, for the single phase full bridge inverter circuit, the output will be switching between Vd, while when the other pairs of switches is on, the output will be equal to minus Vd. So if I am having a pulse, okay, at the output, okay, that is for Vd, this will be changing its value between plus Vd and minus Vd. This is how it will be keep on switching its value. Now, since coming back to the definition that I had mentioned in the beginning, that why this is called a bipolar voltage switching scheme, because the output voltage is varying between two different polarities of the output voltage, like it is switching between plus Vd, okay, this is one of the polarities, okay, over here, and then here we have another voltage polarity, that is minus Vd, okay, and continuously it keeps on switching between these two values. From plus Vd it will jump to minus Vd, okay, and from minus Vd it will jump to plus Vd, and that is the reason that this type of PWM voltage switching scheme is termed as a bipolar voltage switching scheme. Okay. Okay, now let's discuss the next case, that is of the unipolar switching scheme. So this is a PWM with unipolar voltage switching. Okay, in this particular voltage switching schemes, the switching is not performed pairwise. Okay, like in the last case we had the two diagonal switches were turned to be part of the same pair, and they were turned on and off simultaneously. Okay, this is not the case, but each switch is turning on and off individually. How is done that? Let us see the exact waveforms for that. Okay, so now this is how it looks like in the case of unipolar voltage switching scheme. In this particular case, we need to have the circuit arrangement such that it provides two control signals instead of one. Okay, and basically like we already had this triangular waveform. Okay, and we also had this control signal, the sinusoidal signal. It is basically that signal that we want to produce as the output of the inverter. Okay, so this is what we already had in the case of bipolar voltage switching scheme, but now in this case we have like a negative replica of this control signal represented by minus V control over here. Okay, this is one additional signal that we have to supply to our switching circuit to get the desired result for the unipolar voltage switching scheme. So how does this switching work? Okay, now let us see the relative equations for that. Previously, if you remember, whenever we had this V control greater than the triangular signal, so the diagonally opposite switch is TA plus, and that is the other one was TB minus would be turned on at that particular time. Okay, now in this particular case only this one switch will be turned on, as I have described a while ago, that the switches will not be operating pairwise, but they will be working individually in this particular case. Okay, and this V control is also already this V control is only related to the turning on and turning off of the first pair or the switches connected in the first leg of the inverter. Okay, well, when we have the opposite scenario, that is when V control is less than V triangular, so in that particular case the TA minus will be on in this particular case only. Okay, for the second leg of inverter, that is in which we are having the switching TB plus and TB minus, so the other control signal, that is which is the negative replica of this control signal minus V control. Okay, then when this is greater than the triangular waveform, okay, so in that particular case the top switch of the second leg of inverter will be on. Okay, and when we have the opposite scenario as compared to this one, that is when minus V control is less than V triangular. So okay, in that case TB minus will be on. Okay, we can also verify this from over here as well. Okay, now let us take a closer look at this point. Okay, in this particular case, in this interval, we can see that the control signal, the positive V control, that is this one, is greater than the V triangular. So we can see that the output voltage in this particular case is resulting to be it is causing the TA plus to be on, which has been actually represented over here. That is, we can see that in this entire cycle, or in this entire duration shown by these two lines and these arrows, we can see that when this is greater than this one, okay, so TA plus is on. Okay, while for like when this is less than the V triangular, this brief moment, so TA minus would be on, but that has not been shown over here, in fact. Okay, similarly, for this other control signal, that is minus V control, we can see over here that for this particular case, this minus V control shown by this waveform, that is by this arrow, in this duration, okay, we can see that this minus V control is greater. In this case, you have to just like visualize this thing, that here, since these values are in negative, okay, both of them, they're below zero, so the one that is lowest will be in fact higher in magnitude. Okay, so that is why in this region where we have minus V control, a lesser value than V triangular, so that means that it is greater than V triangular, and that is resulting in the on of the topmost switch of this second leg of inverter, that is TB plus. Okay, over there we saw some waveforms about VAN and VN. Now let us see, let us investigate that how is that possible. Okay, so in that case it was mentioned that whenever we are having TA plus as on, okay, so the value of VAN, okay, that is equal to VD. So let us see that how is it possible when this switch is on. Okay, so you can see that this point is all the way connected to this particular point. Okay, and if we take this voltage with reference to this point, which is being shown by this terminal or this label N over here, the same label or N will appear over here. So for this particular case, with reference to this point, the output voltage will be equal to VD. Okay, and for the next particular case, when we have TA minus equal as on, okay, so we can see that the voltage of this point with respect to this point, since they are both connected with each other directly, presenting a short circuit path, so the potential difference will be equal to 0, and VAN when TA minus is on will be equal to 0. Okay, so for this particular case, the output voltage will be VD when this first switch is on. Similar is the case for the other one when this TB plus is on. Okay, so the potential of point B with respect to this point, and since this is all the way connected to this point VD, and with respect to this this lower end, or with respect to this point, the voltage that will be appearing will be equal to VD once again. Okay, and when this TB minus is on, so again these 2 points will be short circuited with each other, and the output will be equal to 0. Okay, so if I just repeat what I have mentioned, that in this particular case the value of VAN will be equal to VD. Okay, in this particular case the value of VAN will be equal to 0. In this particular case the value of VBN will be equal to VD, and in this particular case the value of VBN will be equal to 0. Okay, so if you want to determine the value of output voltage, okay, that is V naught. Okay, so now in order to determine the output voltage, we need to consider the state of individual switches. Okay, since we are having 2 switches, so there are 4 possibilities that we can have. So let us discuss all of those possibilities one by one to get a clear idea of how the output voltage will be switching and what values it will be having. Let me quickly write these different possibilities. Okay, Okay, so we can see we are having two switches in the first leg of inverter, that is TA plus and TA minus. Okay, written them in a sequence, and then we are having two switches in the other leg of switches, that is TB minus and TB plus. Okay, so we can either have them like the top two switches, the bottom two switches, okay, and the cross combination, the top one from the first leg and the bottom one from the second leg, or the bottom one from the first leg and the top one from the second leg. Okay, so let us say that if these two switches are on at the same time, then these two, and then these two. Okay, so what we will have in each of these cases. Okay, since we already know that for this particular case when TA plus is on, so as we can see over here, we will have VAN equal to VD. Okay, and when TB minus is on, so we can see over here VBN, that is equal to 0. Okay, similarly we can write them for each of this one by one. When TA minus is on, we can see over here, then VAN in that particular case is equal to 0, and when TB plus is on, then VBN is equal to VD. For TA plus, when this one is on again, we'll have VAN equal to VD, and when TB plus is on, so with that VBN equal to VD. Finally, when TA minus is on over here, so again VAN will be equal to 0, and when TB minus is on this one, so then VBN will be equal to 0 once again. Now for all of these cases, since as we have already established that V0 is equal to the difference of VAN and VBN. Okay, so for this first particular case, the output voltage will be equal to VD. For the second case, the output voltage will be equal to minus VD. Okay, for the third case, it will be same, so the output voltage will be equal to 0, and again for the final case, the output voltage will again be equal to 0. So in this case, we can take a note of that when if both the top switches are on, okay, or when both the bottom switches are on. Okay, so the output voltage is 0 in that particular case. So during this case, okay, the output current, if there is any, will circulate through the loop of switches and diodes. Okay, same will be the case for this particular case, the output voltage will be 0, but if there is any current, that will be circulating through the loop of switches and diodes. Okay, so here are the differences that we can compare with the bipolar switching scheme. In this particular case, we can see that the output voltage is switching between plus VD and 0 or minus VD and 0. Okay, this is slightly different from the previous case in which the output voltage was switching between only these two levels, that is VD and minus VD. In this case, we can see the voltage will be switching between VD and 0 or minus VD and 0. Okay, so this is why this particular voltage scheme is called unipolar, that with respect to the 0, okay, it will be either going up to this level plus VD, or it will be going down to this level minus VD. So that is why this is termed as a unipolar voltage switching scheme. Okay, let us see the waveforms of this scheme. Okay, now we can see over here that this is the pattern of the voltage across these points AN, and this is for BN. Okay, if you want to determine the output voltage, we need to take the difference of the two. Okay, that is VAN minus VBN, as we can see over here, and this is what we will have available at the output. Okay, now also from the perspective of harmonic elimination, we'll see the graphs, or have the comparison of graphs for bipolar and unipolar voltage switching scheme, and even this waveform gives us an idea that to synthesize or to get a pure sinusoid from this waveform is relatively much easier as compared to the bipolar voltage switching scheme. Okay, also we can see the fact that we described that why it is called a unipolar switching scheme, that output voltage is having this jump from 0 to plus VD and plus VD to 0 during this particular interval, and then it is from 0 to minus VD or from minus VD to 0. Okay, so in the previous case we had a total jump of 2 VD because the output voltage for each of the switching used to vary between VD and minus VD. Okay, The other thing that is of more interest, that is the harmonic elimination, which is much better in this particular case as compared to the bipolar voltage switching scheme. Now here is the difference here is the comparison of the waveforms with bipolar voltage switching scheme. This first one is for the bipolar voltage switching scheme, while the second one is for the unipolar voltage switching scheme. Okay, the circuits and everything else is the same. Okay, so in this particular case we can see that it has almost double the switching frequency, okay, compared to the bipolar voltage switching scheme. Okay, and the advantage of doubling or increasing the switching frequency by twice is evident from this harmonic spectrum. Okay, in this particular case the lowest harmonics, okay, appear as sidebands of twice the switching frequency. Here we can see that the harmonics that are appearing for the case of bipolar switching scheme, they appear as you can see over here in the case of like at the switching frequency, and then keep on repeating at the multiples of switching frequency as well. While in this particular case we can see over here that at this point we don't have any harmonics present in this particular case, while they're only appearing at this particular point, and they in this case also they are appearing as side bands. Okay, so this is a clear advantage that we have in the case of unipolar voltage switching scheme as compared to the bipolar voltage switching scheme. The rest of the characteristics of this circuit are also the same. Those same equations that we had for the previous circuit are also applicable over here. It is equal to MA times VD. That is the case when MA is less than or equal to 1. Okay, while for this particular case also, that if we increase the value of MA greater than 1, then the same equations are applicable that we had for the bipolar voltage switching scheme.